Hello, everyone. Welcome to our start of Lecture 3. For 3A, we're going to look at polyprotic acids. But before we get into our polyprotic acids, we just want to do a very quick review of our monoprotic acids that we explored quite a bit more in detail in our previous course. So some things that I think you should just review over from your Chemistry 1101 is to take a look at your strong acids, specifically which acids qualify as strong acids and what are their behavior in solution. For weak acids, obviously if they're not a strong acid, they're going to be a weak acid, and also look at their behavior, their equilibrium behavior, and how we treat them. Specifically, how do we calculate the pHs of the solutions of weak acids and strong acids? How do we use POH in theirs as well? Also, for our weak acids that do reach an equilibrium situation, remember how to function with ice boxes. We'll also take a look at ice boxes here for our polyprotic acids, but it's just a good idea for you to go back and review if you've forgotten how to handle our ice boxes. If you have any questions on any of the stuff that we covered last semester in the previous course, please make sure that you reach out to me, come see me for help, and we'll make sure we get you straightened out. So let's look at polyprotic acids. We looked very briefly at polyprotic acids in Chemistry 1101, but we didn't really do any kind of calculations with them. They do give us a little bit of a challenge because they are capable of donating more than one H+, which makes the calculations not quite so straightforward, but it doesn't have to be as bad as it seems, as we'll see in the future slides here. As you're looking at the polyprotic acids, each H plus that comes off has its own Ka value. So if an acid has more than one acid, say two H pluses to come off, then the first hydrogen that comes off would have a Ka1 value, and the second one that comes off would have a Ka2. It's just given that simply. So generally, the ionization constant for the second and even possibly third H plus is much, much weaker than that for the first. And so a lot of times what we'll find is that the first ionization is the only one that needs to be considered to calculate the pH of the solution. This is a general rule and does not always hold true, but most of the times it's exactly what we need to do. If you have a polybasic base, so if you have a base that can accept more than one proton, this can also be true. But let's look at polyprotic dissociation. A real good example of polyprotic dissociation is phosphoric acid, H3PO4. Now, if we write the dissociation reaction as a single reaction, we write it like this. We have H3PO4 going to 3 H pluses plus PO4, 3 minus. Now, when we write it like this, it looks like all three of those H pluses pop off all at once to give us a phosphate ion, and that every time that we put H3PO4 into solution, we're going to get 3 H pluses. But that really isn't true. You'll notice that H3PO4 is not one of our 7 strong acids that we have listed, and so it's going to reach an equilibrium. And even more so, as those H plus ions come off stepwise, each of those steps has their own equilibria, and so it's going to have a series of equilibria as we go through. What we'll see with our Ka1, Ka2, and Ka3 is that each hydrogen is harder to take off than the previous one. So here we have first H plus coming off, so this would be our Ka1. We have H3PO4 reacting with water, giving us our H3O plus, losing that hydrogen, H3O plus, and the H2PO4 minus ion. So what we see here is that our equilibrium constant is actually fairly sizable for a Ka, 7.5 times 10 to the minus 3. And so that first hydrogen comes off fairly easily. Now, if we look at that second one, we have H2PO4 minus. So notice that we are in equilibrium here. So the H2PO4 can do one of two things at this point. It can either re-react with H3O plus, take its hydrogen back and go back to H3PO4. So if the H2PO4 minus reacts with water here, the water can take an H plus away from H2PO4 minus and give us another H3O plus HPO4 2 minus. And notice the equilibrium constant here. This would be our Ka2, and we have 6.2 times 10 to the minus 8. So the difference between 7.5 times 10 to the minus 3, 6.2 times 10 to the minus 8 is roughly 100,000 times less. So the decrease in Ka is significant, going from the first H to the second H. And if we move on to the third H, going from HPO4 2 minus, notice here we could go HPO4 2 minus could re-react with an H3O plus that's in that solution and reform H2PO4 minus, or that HPO4 2 minus can react with a water molecule and give us another H3O plus and our PO4 3 minus, our phosphate ion. And again, look at the difference in the Ka3 here. Again, we have a factor of almost 10 to the 5 power here, 10 to the minus 5, however you want to look at that. And it's about 100,000 times weaker than the Ka2, and 10 to the 10th times, so 10 billion times weaker than the Ka1. And so if we look at these values, we see that the Ka2 and the Ka1 reactions, while they do occur, they do not contribute very significantly to the amount of H plus put into that solution. So here we look at some various polyprotic acids here, and we can see the differences between the first H and the second H. Even for sulfuric acid, that first hydrogen that comes off is considered strong. The second one is still very strong at 1.2 times 10 to the minus 2. While technically weak, we do generally consider this to be strong as well, and strongly shifted towards the products when it reacts, especially if it's in there with a base, it comes off fairly easily. So we consider sulfuric acid generally to be a diprotic strong acid. Something like oxalic acid, that first hydrogen comes off very easily. The second one about 1,000 times less easy. Our sulfurous acid, you get a factor of 10 to the 6th difference. Phosphoric acid we just looked at. Citric acid is an interesting critter because it's got it's triprotic acid again, and you've got 10 to the minus 4, 10 to the minus 5, and 10 to the minus 7. So these are actually all fairly close together. So this would be a more complex calculation, especially with that second hydrogen coming off. You probably would not be able to ignore it. It's fairly close in acidity to the first hydrogen here. And then again, ascorbic acid, vitamin C, you have a factor of 10 to the 7th between those two hydrogens. And carbonic acid, you have a factor of 10 to the 4th. Let's look at an example here. We want to know what is the pH of a 0.1 molar solution of carbonic acid, H2CO3. We see that Ka1 at 10 to the minus 7, Ka2 5.6 times 10 to the minus 11. So we have our first hydrogen dissociation here. So we have the carbonic acid plus water going to H3O plus the bicarbonate ion. We can set up our ice box. We know it's a 0.1 molar solution, so my concentration of the acid is 0.1. Hydronium and bicarbonate are going to be 0 because nothing's reacted yet. Our change, we don't know what our X is going to be, so minus X, plus X, plus X, as every time one of those carbonic acids reacts with our water molecule, we're going to get plus X of the hydronium and plus X of the bicarbonate. So our equilibrium concentrations are 0.1 minus X, and we have X and X. So we have our equilibrium concentrations of our species that we need to worry about. If we write out the Ka1, remember it's products over reactants. So we have our concentration of hydronium, H3O plus, times our concentration of bicarbonate, HCO3 minus. Those are my products. My reactant goes on the bottom, so concentration of H2CO3, sorry, missing the brackets there. So that's going to be equal to X times X over 0.1 minus X, and that has to be equal to Ka1, which is 4.3 times 10 to the minus 7. So let's go ahead and solve that here. We have X times X over 0.1 minus X is equal to 4.3 times 10 to the minus 7. Now, if you remember from our previous course, this value is very low. So our reaction goes very little to the product's side. And so what we're going to make an assumption of is that this X is much smaller than 0.1 because the amount of shift to the right is so slim that this X is very, very small, probably much smaller than our second digit here. So it moves out of our significant figures here. So it's an approximation. We'll always check it at the end. So if we ignore that x, we have x squared over 0.1 is equal to 4.3 times 10 to the minus 7. When we solve this for these x's here, we get 2.07 times 10 to the minus 4. We see that this is indeed much smaller than 0.1, and it would take our value outside of significant figures. And if we took 0.1 and subtracted this, we would still end up with 0.1 given our two decimal places there. So our x value, if we look back at our icebox, that is the value of the H3O plus concentration. So we can take the negative log of this value and we get a pH of 3.68. All right, so that gives us our pH after the first hydrogen has dissociated, but now we have a second hydrogen that has to dissociate, and this is going to add to the hydrogen concentration that's already present in solution. So before we get a final pH, we have to see how much does that add to our concentration. So we have our reaction here, HCO3 minus plus H2O, going to H3O plus the carbonate ion CO3 minus. So this is our Ka2 reaction. We set up an icebox here, and notice here my initial concentration of HCO3 minus is my value of X from up here. After we did our first dissociation, I created HCO3 minus. And so this is the value of X from the previous reaction because X was its value in the icebox. I also have to carry that value over here for an initial concentration of H3O plus. I have both of these ions present for the second equilibrium resulting from the first equilibrium. Now my carbonate ion is still 0 because the only place this ion comes from is the second dissociation. Okay, so the only thing that changes here is that I have initial concentrations present. My change in concentration is still going to be another X. If you want to use a separate variable so you don't mix them up, that's fine. You can call it Y or Q or P, whatever. So this is going to be minus X, and plus X. So now we have 2.07 times 10 to the minus 4 minus X for my new bicarbonate, 2.07 times 10 to the minus 4 plus X for the new hydronium concentration, and just X for the carbonate ion concentration. So if we plug this into our Ka2 equation, we have H3O plus times CO3 2 minus over HCO3 minus. That's going to be equal to these values from the ice boxes. I'm not going to read all those out. And we get that here. It's going to move that over to the next page and see what we get. We know that the Ka2 value is 5.6 times 10 to the minus 11. It was given to us in the problem. So that's equal to 2.07 times 10 to the minus 4 plus X times X over 2.07 times 10 to the minus 4 minus X. So again, what we're going to do is assume that these values of X are very, very low, since the value of our Ka2 is extremely low, 10 to the minus 11. Even though the values we're subtracting them for is 10 to the minus 4, we have these X's here trying to deal with that 10 to the minus 11. Again, we'll always check to make sure that it is valid. So if we ignore the X's that we are adding and subtracting, it gives us the 2.07 times 10 to the minus 4 in the numerator and the denominator times X for the top. We can't ignore that X because it's not being added. Remember that the reason we ignore these X's is that we're assuming that the X's that are being added or subtracted are much, much smaller than whatever we're adding them or subtracting them from. And we're just going to end up with that value again. So we've solved for our X here. Well, these two values here cancel out because they're exactly the same. It leaves us with just X, and we find a value of X is equal to 5.6 times 10 to the minus 11. If we take 5.6 times 10 to the minus 11 and we were to subtract it from this value, you would still get 2.07 times 10 to the minus 4. And so here we see a value of X of 5.6 times 10 to the minus 11. If we add that to our new concentrations, so those came in a little bit late, a new hydronium ion concentration as we set it up in our icebox is 2.07 times 10 to the minus 4 plus our value for X, 5.6 times 10 minus 11. That is still essentially 2.07 times 10 to the minus 4. Within significant figures that were allowed, it is exactly the same value, and we still get the exact same pH and after the first dissociation. So technically, yes, we did add additional hydronium ions into that solution, but not enough to make a difference. And so a lot of times we are able to ignore that second and third dissociation. But again, you have to look at the values of the Ka2s and the Ka3s compared to the Ka1 to see if they'll factor in. Now, what about the other ions that were in there? A lot of times we're always looking for the pH of a solution, so we look at the hydrogen concentration or the hydronium concentration, but every once in a while we are worried about something else. We may want to know the concentrations of a metal ion or of the anion in there, knowing are we going to have something that's going to precipitate, or is the metal ion going to be an environmental hazard, something like that, depending on the context of how you're doing your calculation. So if we look at the previous carbonic acid solution, and let's say we wanted to find the concentration of the carbonate ion, CO3 2-. Well, in that last example that we did, that second round of calculations found the CO3 2- as X. If you go back and look at the icebox that we set up, we saw that CO3- had a value of X, and so the value of the carbonate ion would be 5.6 times 10 to the minus 11. There we go there.